Good evening, dear all. So let us continue the topic of the same chapter. That is, we are going to place a dipole in a uniform electric field. Now, physics is a subject of words. You break the topic itself into parts, and those parts itself are the words of the question in the question paper. I am saying that we are going to place a dipole in uniform electric field, right? So I have taken a dipole and placed it in a uniform electric field. So what is uniform electric field? That we don't know right now. So we have to first of all understand what is a uniform electric field. This is Dhanu Saraiya going to teach you about the dipole in uniform electric field. Follow my video till the end so that you understand the concept with different types of cases taken once we derive the formula of what we are going to achieve by keeping the dipole in uniform electric field. Okay, so first let us understand what is uniform electric field. Uniform electric field is the electric field which will have the same value throughout the area we have understood or covered. How to represent it? It can be represented by parallel lines which are equidistant to each other. This is a representation of a uniform electric field, which is external electric field, which has come from other charges. It has not come due to the dipole. So we have taken a uniform electric field. In that we have placed this dipole. Consider this pen as a dipole, which we have placed in a uniform electric field. Okay, so dipole creates an electric field that is immaterial right now, that we know, we have already learned. Dipole has its own electric field at a point on the axis, at a point on equatorial plane, that we know. But in spite of that, we have placed this dipole in another uniform electric field which is represented by parallel lines equidistant from each other. Fine, we have placed it at an angle of theta with the electric field itself. Fine, we can place it at different values of theta from 0 to 180. We will discuss those cases also. Right now what has happened, let us see. Now first, as I have already shown you, that if this is plus q and if this is negative q, then it is placed in the electric field, so it will experience a force of QE. So the direction will be same as the electric field. So the force acting on the charge positive Q due to the electric field will be in a direction of the electric field itself. That's why there is no negative symbol there. In physics, positive symbol means directions are same between the two vectors on LHS and RHS. That has to be understood by now. Okay, so this is a force acting on the charge positive Q due to this electric field which is uniform. Fine. Come to this negative charge. We have a force again due to this electric field on this negative charge also. Magnitudes remains the same QE, but the direction is opposite. So on both the charges, whether positive or negative, the force experienced by the charges due to the electric field which is uniform is QE by magnitude, and by direction it is opposite. Force is opposite. So the total force acting on the dipole placed in a uniform electric field is given by F is equal to F1 plus F2, where I have just named this as F1 and this as F2. Fine. Okay, so that I can add their magnitudes taking into consideration the negative symbol also or the direction also. Okay, so what is the total force? The total force is 0. Now this is a question of PYQ numerical. You have to remember that whenever you place a dipole in uniform electric field, the total force, the net force acting on the dipole is 0. Simple. Okay. Now net force is 0, which is to be remembered. See, you have to go back to the standard 11th where you have learned if net force is 0, this is also one question, the dipole will have no linear motion. What does it mean? That this dipole which I kept here will not have a linear motion due to the force experienced by the dipole in the presence of uniform electric field. Because the force on the dipole is 0, this dipole will experience no linear motion. This is also a question asked. Why it does not experience a linear motion? Okay. So remember, because force is 0, it will not experience a linear motion. Dipole will not experience a linear motion when you place it in a uniform electric field. Now, let us see another type of a motion, rotational motion. Now, for rotational motion, what do we require? We require two forces at two different points. Okay? Acting opposite to each other. Just look at this dipole which I am holding in my hand. You consider this as a dipole. If I want to turn it, what do I do? Yes. So what am I doing with my right hand? I am pushing it. What I am doing with my left hand? I am pushing it but in the opposite direction. So to rotate a body, we require two opposite forces as can be seen. But at two different points. I have positioned two different points for the force. So coming back to the diagram, these two forces are at two different points in opposite directions, so they will couple together to form a torque. Fine. And what is the formula for torque? Torque. Last year we have learned torque is RF. I'm just talking right now about the magnitude. R is the distance between the two points of force and F is the magnitude of one of the force. That means R is the perpendicular distance between these two charges and F is the magnitude of one of the force itself. Fine? Okay. So now how do I get a perpendicular distance between these two charges? I will just complete a right angled triangle with plus Q and minus Q as its vertices. This is a right angled triangle. Fine. This is theta. So this is also theta. This is also theta. So then what is this side? This hypotenuse is of the length 2a because any dipole has a distance of 2a which we have considered. So what is this? Opposite side to the angle theta. That's why this side is 2a sine theta. The length of this side is 2a sine theta. For your convenience, I am just drawing this triangle again, so that there should be no confusion. How did we get 2a sine theta as this particular side? It is the opposite side. For math students, bio students, opposite side to the angle theta is a sine theta multiplied by the hypotenuse. If it is the adjacent side to the theta, then it is 2a cos theta. That also we know. So this is 2a sine theta is a perpendicular distance between the two forces. So I will write here tau is equal to 2a sine theta, which is the perpendicular distance between the two forces. Force magnitude is q. E magnitude I am talking about. So now I am left out with this expression. So with this expression, tau is equal to, I'll just rearrange so that I get something what I know. So I will rearrange this as 2aq e sine theta. Fine. Now, if I break this expression into parts, then this is 2aq is the magnitude of P, dipole moment, electric dipole moment, magnitude 2aq. E, I write it as it is, sine theta. Now again, as per the knowledge which we have learnt last year, if we have a sine theta or a sine function in the multiplication, it is a cross product. So as learned last year, from the vector multiplication of two vectors, C is the third vector of the multiplication of these two vectors. If I write the scalar part of it, this is what we get. So this is exactly the same as this, where A is P vector, B is E vector, and theta or sine theta is the angle between P and E, just like theta is the angle between A and B. So I can write here the vector form as P arrow cross E arrow. This is the vector notation of the torque experienced by the dipole placed in a uniform magnetic field. Fine. So what can I write its direction? If I look at the right hand rule, direction of tau is normal. Normal means perpendicular. Normal inwards into the page. So what is the unit of tau? We can derive it here itself. Tau is equal to P E sine theta. So what is the unit of P? That is the dipole moments unit, coulomb meter. What is the unit of E? By this you can even revise the units. That's why I'm writing. Otherwise directly I can write the unit. Okay, that is Newton per coulomb. That is the unit of electric field. You can even see from the formula, coulomb cancel, and I will bring in the front because it is a capital letter of a name of the scientist. So unit of tau is Newton meter. Now whenever you finish derivation, very important, if it is a vector, understand where is a vector, which rule are we using? We are using the right hand thumb rule, right hand rule. Fine, we are using this, by which we have got that the direction is into the page. Fine. And unit also you have to remember. Even if you have forgotten the unit, individual units, if you remember, you can derive the unit also in the paper. So this is also again a concept to be remembered, a point to be remembered. Fine. Okay. So you just click the picture of this page as I move from here.